Hello everyone, and a very, very warm welcome to Kognito Key. I am absolutely thrilled to have you here today. So, I want you to think of your computer CPU just like a grand, magnificent orchestra. You've got all these brilliant musicians, right? The different hardware components all sitting there ready to play. But without a master conductor, well, it's just noise. So today in this explainer, we are going to explore that very conductor, the control unit.
Okay, let's dive into what this conductor actually does. The control unit is the specific section of the processor that is completely responsible for generating what we call control signals. Now, you can think of a control signal as the conductor's baton. It regulates operations and basically coordinates every single component, ensuring that everyone plays their part at exactly the right microsecond while an instruction is executing.
To really wrap our heads around this, it helps to divide the whole instruction cycle into two main phases. Think of it like a two-part play. First up, during the fetch phase, the control unit reads the instruction and fires off those absolutely crucial control signals. Then it hands the heavy lifting right over to the execution phase. This is where the actual computing, reading of data operands, and storing of the final results takes place, which is usually managed by the ALU.
Now, executing just a single instruction happens in 5 highly sequential steps. We've got the instruction fetch, then decoding, operand fetch, the actual execution, and finally operand store. And here's the really interesting part. Every single one of these steps takes exactly 1 clock cycle, with the system using a step counter to keep track of its progress. But most importantly, each individual step needs its own very specific set of control signals to even happen.
Which of course brings us to the million-dollar question. We know we absolutely need these vital control signals for every single tiny step of the process. But how do engineers actually design this conductor to generate those signals inside the machine?
Well, historically, CPU designers have basically come up with a tale of 2 entirely different approaches to solve this: hardwired control and microprogrammed control. It's essentially a choice between a very physical logic circuitry approach versus a memory-based software approach. Let's break them down.
All right, let's look at approach number 1, hardwired control, which is the physical logic circuitry approach.
You see, instead of using software, this method relies entirely on physical hardware logic gates and circuits to generate those control signals. It's built to react instantly to 4 specific hardware states: the status of our step counter, the actual content sitting in the instruction register, the output from any comparison operations, and external signals, like system interrupts. The hardware just takes all of these physical inputs and bam, instantly generates the right signal. Because it is completely, literally hardwired into the physical circuitry, it is unbelievably fast. Think of it like a musician playing purely on raw instinct. And that speed is exactly why hardwired control is the preferred method for generating signals in RISC-style instructions. That stands for Reduced Instruction Set Computer Architectures, where blistering speed and absolute simplicity are the top priorities.
Right, let's move on to approach number 2, microprogrammed control, which is the software approach.
Imagine if, instead of being physically wired to act on pure instinct, our conductor actually used highly detailed sheet music. That's essentially what a microprogram is. It's a special control program stored in a dedicated control store memory. This microprogram is made up of micro-instructions, which we also call control words. Every single bit inside one of these control words dictates the exact control signal setting needed for a specific step in the execution flow. It reads the word, and it sets the signals. It's that beautifully simple.
Let's trace how this flows, because it really is a highly coordinated story. First, the instruction is decoded in the instruction register. Next, the micro-instruction generator loads the starting address of the routine right into the microprogram counter, or the MUPC. Then, that exact address is used to read the specific micro-instruction needed for execution directly out of the control store. And finally, the MUPC just increments to read the very next micro-instruction in the sequence. Now, because this approach relies on a sequence of micro-instructions stored in memory, it is incredibly flexible. You can literally change the sheet music without having to change the whole orchestra. This amazing flexibility makes microprogrammed control the typical go-to method for generating signals in CISC-style instructions, and that's complex instruction set computers, where instructions can get a whole lot more intricate. So putting them head-to-head really reveals a classic engineering trade-off. Hardwired control is blazing fast because it uses that physical logic circuitry, but it's very rigid, which makes it perfect for RISC. On the other hand, microprogram control takes a little bit longer because it has to read from a control store memory, but its incredible flexibility makes it an absolute dream for complex CISC architectures. So, What's the verdict? Which is the preferred way today? Well, the source material gives us a very clear modern winner. You see, producing logic circuitry has become so incredibly cost-effective and highly efficient over the years that it simply doesn't cost much anymore. Because we can have all that immense speed for such a low cost, hardwired control has become the favored, preferred choice today for designing a modern control unit.
And there you have it, the master conductor of your CPU completely demystified. But, it does leave us with a pretty interesting thought. As artificial intelligence pushes us to design entirely new kinds of processors, will hardwired control keep the baton? Or is a totally new, unseen approach waiting in the wings? Thanks so much for watching. Don't forget to subscribe to Kognito Key, like, and share this explainer. Keep learning, keep exploring, and we will absolutely see you next time.